Hey guys, um, already saying hello. We will start in what is it? 2 minutes, but just want to say already hello, like check if the audio is working and stuff like that. So yeah, is the audio fine, or is there like some noise going on? Okay, nice. Audio is good. Good. Okay, 2 more minutes. And also, hello, Kelvin. So let's see how many people show up now. We also did a stream like 2 days ago because we had like 2 meetups this week, and the previous one had like 30 people at the max, I think. But I think the average was like 15 people, so we'll see like how many people show up now. And also, Kelvin, do you already have experience in machine learning? Let's see. So 1 more minute. I'm starting to get into Python, did some automation. Okay, cool. Oh yeah, I think it's already time. I also see that there are just 5 people at the moment, so I want to check if the stream is fine. Apparently you guys are here, so it should be okay. Let's just check for sure. That seems to be fine. Cool, okay, well, then I think we will start. You can see, can you see me? I can see your chat. That's about it. Yeah, so let's just start. Great. Okay, cool. I forgot to put the topic over here. Oh well. Yeah, so we will talk about machine, like deep learning in general, and more like also regarding the different architectures that are there. Like with deep learning, there are like so many different things you can do with deep learning, and it seems to be like something like magical, but there's actually like logic behind it. So yeah, we will talk about that. First, a little bit about us. So we normally host like 3 meetups a month pre-Corona time. So we thought like, oh hey, now we can probably do some more meetups because Corona's like getting lower, the numbers. But apparently they were rising again, so we thought like, hey, let's just move the meetups. We were planning just put them online. But yeah, we hope that if Corona's over, we can actually do the live ones. But I think they're really fun. Like there are many different people coming, and it's really fun. So yeah, what else? What else about us? Yeah, so we give lectures or like courses in machine learning, deep learning, data science. We mainly do that in data and Den Haag and Rotterdam, but also sometimes Rotterdam and stuff like that. So yeah, the layout for today. First, I'm going to talk a little bit about use cases of deep learning, and then I will talk about deep learning one-on-one, like what is it. Then talk about data, like the inputs and outputs of a model, like how it looks like. And then I will show you a couple of shapes of deep learning. And then I want to test you guys, like to see if you can kind of like guess if a model will work, yes or no. Well, oh yeah, so maybe chats are just 6 at the moment, but can you also like give some examples of deep learning you can think of? So just put in chat some examples. I have a 10-second delay, so I will probably see them 10 seconds after you post them on the chat. But yeah, which kind of examples of deep learning can you think of? Let's see what you guys can come up with. Okay, I think you may be already typing, so I will already kind of like Okay, like image recognition, yes, for sure. That's like a big thing, of course, with deep learning. It's really good at images. Yes. Yeah, so if you have more examples, you can just say it. I will just show you a few, which are like really fun. Looking for cats in pictures, yes, indeed. Yeah, indeed, object recognition like cats and images, of course. Yeah, so with images, like also kind of where you're starting off right away. Yeah, if different things. For example, this one is object detection. So let's maybe put off the music. Yeah, so you can see here and also example of object detection, which is called YOLO or YOLO 3, which is the newest one, official new one. Which detects like many different things like cars and people. It's really doing really well. Pattern recognition, yeah, for sure. Like everything deep learning is doing is like pattern recognition. Like patterns can be everywhere, like in images, in text. So for sure, like pattern recognition, I think that's the main thing you're doing with machine learning in general. Yes. Another thing which you can also like do with images is image segmentation. For example, you see here person 1, here person 2. There are multiple cars. That's called image segmentation. Yeah, it's also like really fun. Also other things, you can also like do image generation. I think it's really cool. So let's show you a few examples of that. So I really like this one. You can also like go to the link if you want. So you can, let's say, generate some pictures. For example, here I maybe, okay, let's put some dirt over, let's put some dirt over there. Hop. And let's go for maybe some grass. Let's put grass over there. And what else? Rocks. Here are rocks. Like rocks over there. Maybe also like a rock over there. And maybe a mountain like a little bit far away, like that. Yes, so let's generate and see what you get. And you get this kind of landscape, which is really nice, which is really cool. See, like rock over there, grass here, rock over there, and there. This is apparently a mountain. Yes. You can also maybe make it a little bit better. Maybe put some rocks. Oh, stone. Okay, sure, why not? Stone over there, and you'll get some additional stone. So cool. Yes. Yeah, this is one of example of image generation. Whoa. Now what else? Maybe you also know this website. This person does not exist. So I can just F5 a couple of times, and you always get a different image of a different non-existing human, which I think is really cool. They are also like generated with deep learning. Yes, so image generation. I think I want to go full screen again. No, I went a little bit too far. Other things you can do is like with text. So BERT is a model which can do text analysis mainly. That's really good with BERT. And you also have another one which is pretty popular nowadays, is GPT-3. And this one is to generate text, which is also like one of the models I use for one of my latest projects. Yeah, indeed, house price analysis. I think that's like one of the textbook examples to start with machine learning. Yeah, for sure you can do that indeed. Yes. Yes. What else? Reinforcement learning is also something I really love. I think it's really interesting. It feels a little bit more like how maybe like a general intelligence should behave, like learning from their own experience. So reinforcement learning is learning from punishments and rewards. So just like we also get punishments and rewards during our life, that's also like how reinforcement learning works. And they use that to make an AI which is really good at Go, and also an AI which is really good at moving fingers and stuff like that. For example, this robot here is solving a Rubik's Cube, and it's also learned reinforcement learning. Yes. So I think those are really cool. I really love reinforcement learning, but they're like pretty hard. I think with machine learning, if you want to start with deep learning, I think reinforcement learning are the most fun. I think I also started with deep learning with reinforcement learning, but they're also like a bit harder because you have a lot of extra stuff. Cool. And also like recommendation systems, of course. This is more like practical also. Like a lot of websites like Facebook and Spotify, they also use like machine learning, or also for sure also partly deep learning to do recommendations. Yeah. So what do those networks use? like I said, most of the time deep learning. So I will just go briefly about like what deep learning is, just to be sure that everybody knows a little bit about it, like the base. So yeah, deep learning or artificial neural networks, they're like they are very closely linked to each other. Not the words are not the same, but they're like the difference. But most of the time, if you talk about artificial neural networks or and you also talk about deep learning, yeah, so they're based on the principle of how brains work. So let's say we have here three brain cells, where this part is the input of the brain, and this part is the input of the brain cell. This is the output of the brain cell. And you have three neurons here. Neuron is, by the way, a brain cell. And the output of this neuron is connected to the input of this neuron, and the output of this neuron is connected to this neuron. And most of the time, probably neurons are chilling. They are not firing. And maybe there's something going on. Maybe you're thinking about a car, or maybe you're seeing something with your eye, and one of the neurons gets triggered. Then maybe this one's not getting triggered, but maybe if the other one also getting triggered, then this one will be triggered. So it's kind of like neurons are like adding and subtracting signals to determine whether or not they should also fire. Also, like neurons they also can have negative or positive effects. So they're quite complicated, but this is also, of course, a one-on-one. Yeah, and they also have, let's say, like with neurons, they fire or they don't, and they have, let's say, chance that if they get enough input that they will fire. So neurons can only be 1 or 0. They don't have in the between value. Yeah, so let's also like explain how this would probably work in a computer, or like how they actually kind of simulate-ish. No, not simulate. How they kind of like put the same idea in a computer. So let's go for this example. Let's say you want to have a model which predicts if you have to eat frozen pizza today, or if you want to go to do some cooking. And maybe your parameters to determine if you want to do that is your laziness level, the number of days ago you have last cooked, and if your parents are coming over. So let's say you insert the input. Oh, yeah, also like every node is, by the way, a neuron, and yeah, like this. So apparently like 3 neurons, these 3 are the input. These 4 are the hidden layer, it's called the middle layer, and these 2 are the output, like this. And also like the connection, so this arrow here indicates that this one signal is going into this one, and this one's output is going to this one, and stuff like that. So yeah, let's say you insert your input of that day, and maybe you're feeling pretty lazy. You have recently cooked, and then the neural network will do its calculations layer by layer. So first layer, then second layer, and apparently you will eat frozen pizza. But maybe there's some new data, and let's say your parents are coming over. Then you have to once again calculate over again the hidden layer and then the output layer, and now maybe you have to cook today. So that's kind of like the general idea how a neural network works in a computer. Of course, at the moment this is like kind of like magic how I explained it, but of course there's some math behind it. So the math works like this. You have every neuron has, let's say, its favorite. So for example, this neuron is, let's say, weakly linked with this one, and maybe this neuron is kind of half good, properly linked with this one, and weakly linked with this one. What it will do is it will multiply this value with this value, and this value with this value, and this value with this value, and will add all those 3 values together, and it will determine this one. Of course, it's not the whole story, because it also has a bias, which is kind of like an offset of the value, and also an activation function. And this activation function gives the dynamics of the model. And this is how a whole neural network works. Like, of course, the most basic one. But like, if you know already this one, then you're already good to go. And of course, these values, they feel like magic at the moment, like where do they come from? So if you have a neural network, you always have to train it with examples, and those 4 values are, let's say, trained during training. Of course, there are way more, so I just only highlighted 4 of them, but like every arrow is 1 weight, or like 1 trainable parameter. So if there are any questions, you can just ask them, that's fine. Yes, so if there are no questions, I will just move on anyways. And if you have a question, I will probably just go back and talk about it, because like I said, there's a delay in the stream. Yes, so let's go and talk about inputs and outputs, because like we have many different things we can put into a neural network, like values of a patient, like the blood pressure, sugar level, heart rate, or like also someone else mentioned the price of houses, or like parameters to determine house price and stuff like that. But also like images, also text, like this is a sentence, like text, you can also insert that in a neural network, and also like stock values. And also some outputs of a neural network can be actions, like go left, move your arm, and stuff like that. And also you can also insert music or sound in a neural network. And they seem to be so diverse, like how can a neural network do that? But now, well, we can also do it with our brain, so maybe it's not that weird that it can do that in some way. Yeah, so if you want to do that, then you have to change everything into numbers. Like computers, they can only work with numbers. Yeah, here I just display ones and zeros, but of course in a computer you just handle numbers like 5, 10, whatever. -1 is also fine. Yes, so you have to change every value into, or like every data item into numbers, and that's something you can handle with deep learning. So let's go for the easiest example. Let's say values like patient data. The only thing you have to do is just normalize them, and you can just insert them in a network. So they're like really easy. That's the only thing you have to do, like normalize them, and you can just insert them. With images, it's also pretty straightforward. Like an image is already numbers on its own, right? For example, you have an image. An image is actually a RGB. There are actually 3 images, which one is R, the other one is B, and the other one is G. So there are 3 images of 3 different colors. The only thing you have to do with that, and once again, is normalize it, and you're fine. Text is a bit harder. Text is not like something which is really easy to assign a number. So we have to do some pre-processing first. So in this example, I have this sentence. This is a sentence. And the first thing you have to do is you have to split the things into separate entities. And then you have to give those all a value. So for example, I give the word this number 5, the word is number 3, the word a 2, and stuff like that. Yes. And then what you can also do is give them all a vector. And a vector means that like every word will have, every word will be represented in a space where words which are very similar are close together, and words which are way more different, they're further away. So yeah, this step is maybe not that easy to understand, but you want to have that the word swim and swimming and swam, those 3 words are pretty close to each other, and then you can do embedding to make this work. What else? Yes, also sound. I also said that you can also insert sound into a network. One thing you can do is make a spectrogram. So you just map the frequencies against time, and then you actually have just an image back. And you can also, just like I showed you before, you can also insert an image into a network. Yeah, action. You also have to, yeah, so there are 2 different actions, or, yeah, I mean, there are many different actions, of course, but there are 2 different ways to work with actions. So you can make them discrete. So you can just do like do this, do that, or you can make them continuous, meaning that you can maybe like move an arm, like you have like 90 degrees or 180 degrees. So you have to also like think like, do I want to have to be continuous or discrete? And like discrete is easier to train, but continuous of course has more freedom. Yes. So yeah, this is only steps required to make everything into numbers. So like just to recap how like all these things. So I showed you how to just work with normal values, with images, with text, with sound, and with actions. You can all turn them all into numbers, and then you're all good to go. Yes. And of course, then you can of course go and work on to getting world peace with your networks. Yeah. So how does this actually work? Like we now have everything into put everything into numbers. But now maybe the question you have is like, do you treat everything the same? You just have one big network, and will you just insert all the values and you just get your result out? Well, it doesn't really work that easy. Like you can also see on this image, there are like many different networks. So the one I showed you before was this one, the feed forward. But as you can see, there are many more networks, and every network has their own pros and cons. So if you always have to think about, okay, I have this problem, so I have to have this architecture. And you can also see there are multiple different colors. So the ones I showed you are the input, the normal one, the normal cell, and the output. But you also have things like recurrent networks, convolutions, and stuff like that. And this picture is for sure not complete. Like there are way, way more things than just this picture is describing, but it looks pretty, so that's nice. Yes, so these are some shapes I drew, and we are going to talk about those. So yeah, but I will talk about later. So the one I showed you before is like feed forward. I just described it like this. So you have just an input, you have some neurons and an output. But as you can see, you have many, many different shapes, and they all have, let's say, different functionalities. Also, normally I also have a break around this time, but because like online everything goes faster anyway, so I will just skip the break, and I think we have just a longer session afterwards. Yes, so I'm going to give you some questions. So I will show you a problem and a network, and I will wait on the answers. You can think of like if you think that the network will work. So if you think that the model I showed you works with a problem, then you just say it's all good. And if you think that the model is not good, then you have to just say in the chat that you don't think it will work. And yeah, then afterwards I will say if it's not good or good, and then you have to like say like why it's not good. I'll see some questions. How can you have multiple inputs? Input layers. What is the Z standing for? Multiple input layers. Oh yeah, good one. So this one is recurrent neural network, and in this case, it has this network will accept one input. It will do one calculation and another input. So that's why I also like put this symbol over here. So you will have one input, it will do one rotation, we'll insert the second input, one rotation, the third input, one rotation, and so on till every input is, let's say, inside the model, and then the model will continue. That's like one thing the recurrent neural network can do. And the Z, yeah, the Z, it stands for latent space. So a lot of people, like in a lot of cases, they call the input the X and the output the Y. And in a lot of cases, you have, let's say, the interesting features, they are emerge in the middle, and that's called the latent space. And they always give the letter Z to the middle. Yes, so yeah, those are the main ones. And the sigma symbol here indicates that there's noise. So this model works with noise, and this is kind of like, this is a kind of also like an output, the D, but it's more like it lets reinforce if something is good or bad. So it's kind of like an output, but a little bit different. Yes. But also, like, you can also have a neural network which has multiple inputs at the same time also. So you can also like have an image and sound and temperature value. You can also insert all those three in one neural network in one go. It's also something you can do. Is the multiple input the same? Is the multiple input? So if you use backpropagation, then also like yeah, it has so like I said, and you insert one input, then the other one, then the other one, and also like the backpropagation also has to do, let's say, the same round but back. So the first word which is inserted also has the longest path from the output. Yeah, so let's go to the game. So I will, just like I said, I will show you a problem and a model, and you guys have to say like if you think it's a good match or a bad match, and then you have the chance to say like why you think it's good or bad. So first one is a simple one. So let's say you have data of a patient or house price, that's also fine, and you want to determine if that patient is sick or not. Like let's say you have a specific disease and you want to predict if that patient has that disease. Do you think that this model will be a good fit for that problem? So I will wait for a few answers, and if I get a few, then we will then I will show you if it's a good or a bad fit. kind of annoying that, of course, everything has a delay, but oh well, I have to live with it, I guess. So also, like, if you have the chance to go to the end of the stream, maybe that works, then you can also like give an answer faster. Okay, I already have some answers. Not good, but I think the principle is a good fit. Okay, I don't think that one. Okay, I already have 2 answers. I'll wait like 5 more seconds, and then I will go into a answers. Also, like if you already want, you can already give the reason why you think it's good or not good. Okay. Okay, I will just give me my answer. So I think this is pretty good. Like, if this is a pretty simple problem, you can just insert the parameters here. So you can just insert like if the age here, the blood pressure here. This is a pretty simple problem. Like, you can maybe like argue that one layer is not enough. I can kind of like agree that that might be the case. But if it's a linear problem, like if the data is not very exciting, let's say, then this is already good enough. The output, of course, if someone is sick, that should be the output. Why did you think it was not good? Yeah. Yeah, so indeed, like you can also like give an answer why you think it's not good. I'm curious to know. But I think this is a pretty good fit for this easy problem. Well, you give a reason, then I also like continue. This is the second one. Let's say we have images and we want to classify if it's a dog or a cat, or in this case I called it a good boy. So do you think this model will be good enough to classify if an image is a cat or a dog? And I'll also give you some time to think about that one. I also see a good answer like the Prabhu. I also see you like saying, yeah, you're kind of saying that you think it's too complex, the model, in some way. And I kind of agree. So this really works like a neural network in this case. So this model does work, but I do agree that a way simpler model would already have been good enough. So I do agree with that. But this one would also work. Let's go to this one again. I think no, it requires image recognition. Okay. Okay, I already see some good answers. Yes, so I would also think that this would not be a good fit. For sure, indeed, it's very short. So I do think that if you make this network really, really big, it would probably work some way, but it would be way too small. Yeah, but you can also be a bit more smarter. So what I would actually do in this case, like if you want to do object recognition, I would use a different network. Yeah, also like the 2 different things. So like the relation, like yeah. So like one thing indeed, like this model is not big enough. Also there's too much data inputs. Like the image is pretty big. So to put every pixel value in every color in the input will be really demanding. And also like one thing which is lost during doing this is that the relationship between pixels is gone. But if you make this one really big, I think it will do pretty decent still. Okay, how will it work? So yeah, also like how this could work, you would just insert one, let's say you have 1000 pixels or something, then you have 1000 pixels and 3 colors, so you have 3000 different values. So from every pixel you have 3 values. And you will just insert, let's say, the red pixel color value here, the blue pixel value there, and stuff like that. But you have way more. Oh yeah, also one thing, this one would be way longer. So yeah, I didn't redraw that one. It's a good one, but this model must be way longer. So I just put it here like simple, but yeah, the width must be longer for sure. Yes. But then you just put all the pixel values in here, and I think indeed you have to do more layers for sure. But I think then it would do pretty well. But what I would actually probably do is use a convolution network. And convolution networks are smarter networks. So what they do, convolution networks, they look locally first. So you actually kind of have a network which is first doing some calculations locally on the image, and then you kind of like zoom out. So here I just drew 3, but normally you will do probably more. For example, you have this model, VGG19 or something. You also have other ones like ResNet and yada yada. Let's go for this one. So for example, this is VGG19, which is kind of like the same one I drew here, but of course way less layers. But here this one has 2 different convolution networks, meaning 2 layers which are looking locally. Then max pooling, which is something which makes the image smaller. I could also talk about that, but it just makes the data smaller. And then you have another 2 convolution networks. In total, you have 1, 2, 3, 4, then 8, which is, 4 I mean, that's 8, plus 4 is 12, plus 4 is 16. So you have 16 convolution layers, meaning that 16 times you're looking locally and kind of making the image smaller. So that's this process. And then it has 2 normal hidden layers, and then the output layer. So it's kind of like this. And this one works for object recognition. This is how you actually can make an object recognition thing, or image classification. That's the better term, because object recognition can also like most of the time say like where in the image you see that object. So yeah, cool. If there are any questions, you can also like ask them. Not good. Yeah, but indeed, like good to. It's indeed a good thing that you indeed need more layers for sure. But like I also now showed you, there's also like some other smart things you can do is adding convolutions. Is there a science behind deciding the number of layers given a problem? I think a lot of times it's kind of like try and error. That's also like why if you just look at the challenges, so let's say object recognition, let's go for a graph. You also have ones which has a year assigned to it. Let's see. I want to see years, because like also models are also released in different years, which was kind of fun to see. I want to have a few with a few years. Object recognition, object classification. This may be better. I cannot make a final image with as a years as well, but like there are many different models you can see. I think maybe also like some shapes are like bigger or smaller, so there's like really like a kind of like progression on the years, like which model is better. And for example, here I showed VVG 19, but you also have its brother, which is VVG 16, and they're both used. So the pros of VVG 19 that it's better, it's a little bit better, but VVG 16 has a benefit that it's faster. So of course bigger models are slower and smaller models are faster. So that's also like why there's, let's say, yeah, it's not that clear cut how many layers you should also take. Also depending on your own desires. But you also have like another one which is called ResNet, and that one is a bit more weird. So this one has more layers, but it also has skipping layers to also like give some weird that it's that will also help gradients go through. So you also have, let's say, weird adaptations to this whole object detection. And what does the VGG stand for? Good question. VGG, let's see. VGG stands for very deep. Wait, is it really like very deep or something? We really funny. It indeed sounds like very. I don't know. Huh. Good question. What is stand for, maybe I get an answer like that. Oh, visual geometry group. Really? Huh. Wait, no. Wait. Model. Probably this will be better, right? I think that VVG can also stand for other things. Very deep. Oh, here's. I can already find it. It says a lot of times very deep convolution network for large scale image recognition. I don't know. You can maybe look it up. But it's a good question. But yeah, so so like so this is the whole mechanism I would probably use, and the one like VVG 16 and 19 are based on this one. But you also have other adjustments which are more creative, like the ResNet I showed you. ResNet, that's one which is like a little bit odd. You also have those, and it can also improve the whole model. Okay, so let's go to the next one. Let's say you have this problem. You want to turn an image of a horse into an image of a zebra. Do you think that this model over here would be good enough to do it? And also, would it be practical to do it like this? I also want to know your answer about that. Do you think it's a practical model to use this to generate from a horse image a zebra image? And also like why or why not? So maybe also can I elaborate what's happening here. So here you have just a network which does a lot of operations on the image, and then it makes it, let's say, and during those operations it makes it smaller. So those can be convolutions, and then we'll make it bigger. So yeah, that's the network I described here. So do you think it's a good model to use this thing or not? And why? Do you use one horse? So also like, yeah, a good question. So you have a database of many horses and many zebras. And let's say you have a data set of 100,000 horses and 100,000 zebras. And you will train it with that data set. And then you will try to make the model be able to turn all the horses into zebras and zebras into horses. But then of course you need another network as well. But maybe, okay, so you just only want to turn the horse into zebras, let's say. But you have of course a large data set. So who else thinks if it's a good or bad network to do it like that? Okay. That's an interesting thing, because that's something which is going on as well, like also what Kelvin says. So I think you need a zebra to horse layer and then a horse to zebra layer, and that's really interesting because it's pretty close. Okay, so I will give you kind of like answer. So I think this would not really work. It could maybe work, but like, how would you train this? So if you want to train a network, you need to have the truth and the answer. So if you want to train this, then you need to have an image of a horse and the exact answer. So let's say you have, this is the input, and you need to have the output, and only then you can train this network. So if you want to do this, then you need, let's say, a whole team to manually change all the images of the horse into zebra, and then you have a good data set to train it. However, this is really hard. What you can do, however, is something else. This is like what I said before. you do not have the images of the like, you don't have images with the exact same, let's say, the exact same spot, the zebra of the horse. So you really need to, let's say, have a the truth, but you don't have it. Yeah. So what you need is something like this. So what you do is you have here you insert the image of the zebra, and you have a network which changes into a horse, and then you have a network which changes this to a zebra. And then what you will do is you will compare if this whole operation that it managed to reconstruct the zebra. So it will compare this one with this image, and it will check if this picture is a picture of a horse. So this will work because you do not now need to have the true image in the correct form. So now, because you actually you apply the transformation and then you reverse it. So you only need to compare those two images now, and you only have to check if this one is a horse. This one is most definitely the hardest question I'm going to ask. Like, this one's really, really hard. But this is a network which would work, and this is actually called CycleGAN. However, there's also like one small adjustment, and that's because like here the image becomes smaller, 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 and then bigger, bigger, bigger again. But then it loses its finer details in the image. So that's why you would actually need a different network, and this is called UNet. And this is also a network which will also which will make the image smaller, smaller, smaller. And at the same time, it also has an additional path which will map, let's say, the inputs to the output layer. It's a complicated one. You can also look it up. So it's called UNet. So UNet is able to both analyze the big picture and the small features. And the GAN system, which is also here, which means that you this is the GAN system here. So you have an image and you see if it's a correct one. So this is a GAN part, and here you also have a GAN part. And this part is the UNet part. And this is a really clever one. So like I said before, this model is called CycleGAN. So I can also maybe like show you guys. YouTube, CycleGAN. Here. Okay, good. Do you show CycleGAN? Or are you just going to talk about it? Okay, he's just going to talk about it. CycleGAN, horse to zebra. Here. So this is using CycleGAN again, and actually you insert a video here and can actually make it into a zebra. And like, the result is kind of like questionable, I agree, but it's really pretty darn impressive that it can actually manage to do this already. Yeah. Okay, cool. Well, also good, Kelvin, that you also kind of realize that you maybe also need another network, so that's good. Another one. So let's say you want to have a network which compresses an image. So let's say you want to make something like WinZip or something, but specifically for specific images. Do you think that this network would be good to compress images of a certain type? So also, to explain how this model kind of works, you insert the image here, and it goes through a network, and it will hopefully predict the same image back again, and you will compare it with the original image. Do you think that this model would be good enough to compress images? Okay, Kelvin thinks it's possible, but I think he thinks it's probably still magic. Yeah, it feels really magical, I can imagine that. So if you maybe like also want, I can also like show you how to do this, because I make these networks a lot of times. But yeah, it's for sure possible, so I will approve this one. I actually also made this network myself, so I also have my own website, which I do my own projects. It's... yeah, not sure, but I think it will not work because JPEG. Work with JPEG. Oh, for sure, it will not work with JPEG. So you make so you make your own compressed network. So it will not be indeed like JPEG, but it will make its own compression. So I will like show you what I did with this. So let's go to this link over here. Oh, I know. So this is my own website. Oh, I have to go to Firefox with this one. Here you go. So, and voila. Because my Chrome, it crashed one library, now I cannot not use it here. So what I did, I trained a neural network to on a computer game, Doom. So I just showed it many, many different frames, and the only task was to actually use this network over here. So this network over here, it just had an input, a frame of a game, and had to compress it, and then had to make the original one back. So that's what I did, and I did for many, many times. I think I trained for like for 1 day, and after a while I could do things like this. So I could move the shoot neuron. So what I do here, I highlighted 16 neurons in the model. So those 16 neurons are the ones here. So the Z layer, this is my compressed layer. So in this case, I have 16 neurons in my Z layer. So the latent space. And those 16, I actually put those values over here, and I can change them. So so if I do this, it shoots, and now I put it back again. And I can also do other things, like I can also like change something with the hand. So it is like something with the hand. I have no idea what it's doing, but something with the hand. I can also, well, let's do the gun a little bit better. Yeah, there. Walls, I can also move the walls. And this is all, it learned it himself. So I did nothing like, so those neurons, those 16, it learned by itself to be able to do this. So I just gave it the input image, and it has to reconstruct it and kind of like magically kind of drive this. So I can like move the walls like this, and also have a button over here. So let's say I'm closing to this wall, and then I can drag this one, and it actually nears the wall. So it's kind of like funny. So this slider is for closing to the wall, and this slider here is to go to the other wall. And then I can close this one as well. There was also actually a monster. So here you can still see the monster. So it was not able to learn the monster position, which is kind of annoying. Yeah, so also by the way, if you want to know like why I did this. So then I used another network to make another one. This one over here. So I actually made a game where you can now just like play it, see? And this is all done with the neural network. It's kind of like fast, so I just make it a bit slower. Now it's slow. So now I can just like go right, go left, and shoot, go left. And it's all, so what I do here is I kind of like mapped actions to the latent space. So I changed the latent space, and it renders a different frame. That's kind of what I did here. It was like a fun project. I also made a video about it on YouTube if you want to know how it works. Yeah, maybe I can also like show you. YouTube, let's see. Maybe like wait. So if you want to see the video about how it works, so here I made a video. This is my YouTube channel. Like how this actually works. So if you want to know how this whole network works, here I explain this whole network, and also like how what I did during training. But yeah, okay, cool. Let's see if there are questions. Are you sharing a different screen? I hope not. Was everything working? I hope it worked. If I do Firefox again. Wait, I think it should be fine, right? You're right. It didn't capture. Wait, you're correct. Okay, damn, you're right. Okay, I will show you again. Wait, Rix projects. Thanks for telling me. So here, I will just do it again. Yes, now you can see. So here I made this thing where you can just slide along in the latent space, and here you can see that it moves the weapon. See? And this is the latent space. So this is one of the neurons, but there are more neurons. Like for example, we can also like move the hand. There's another neuron, and what else? You also have this one, which is the wall. So here I can change the position of the wall. And here I can go closer to the wall, further and closer to the wall. And now I can go back to the other wall and close to this one. So this is what I did with the neural network over here. So I just had this frame of a network of the game, and then had to reproduce it. And so yeah, and then I had the game, so I made a game out of it. So here I can just play it. Let's just like slow it down a bit. So here I can now go left, I can do shooting, I can go right, and do more shooting. And this is all done with this neural network and also some other neural network. And like I said, if you want to see like how this one works, you can just go to this, where is it? This video, and I kind of explain like how it works. So if you want to do that, but it's up to you. Yes, but thank you for saying. I I didn't know. Apparently, I shared indeed the browser instead of the screen. Thank you. If there are any questions, just mention them. So yeah, I approved this one. So this is a good one to compress images. But of course, it will not be like JPEG, but it will compress it in some way. And like, yeah, maybe also like to recap. So, so it compressed this, so it compressed the whole image in just 6. Wait. Oh, yeah, of course, this is Chrome, but it just compressed the whole image in 16 different values. So it compressed it by a lot. So it's kind of nice. But of course, they are very custom, so they don't work on different images. Are you the first one to make the Doom game neural network? No. I think there are way more people who already did something with neural network in Doom. Well, I don't know. Not so they didn't make a game generator, but a lot of people are making the Doom game player. But I just the Doom game neural network, I made it, but not the game itself, of course. But I did make the neural network. So like I said, you can just watch the YouTube video, and I show you how it made it. And it was my original idea. Yay, fun. And it actually was based on some other video, but it was like a video generator. Cool. Next problem. So here, let's say you want to translate a English text to a Dutch text. And you have, let's say, this sentence. This is a sentence. And you want to translate this to dit is een zin. Do you think that this network would be good enough to do this properly? So yeah, place your guesses and let's see if you get it right. So do you think that this network would be good for this network, for this problem? But yeah, Kelvin, I thought you just said I was the first one to make, I don't know, I think I am the only one who made a game out of it, like generated the game itself, but more people doing something with Doom with neural networks, but I think they didn't make the game. But well. So yeah, do you think that this network will be good enough to do translation? And if you have no idea, then you can just put in the chat, I have no idea, and I will also accept that. Okay, I already have some answers. Wait 5 more seconds. Okay, I have some answers. So I think this one's actually pretty good. So like this model can do it, but like also you need way more data. So you have to train it, and of course this model has to be trained on many sentences. So you already need to have a data set with the correct translation, and then you can train this model to be able to translate it. And this model will actually do it. However, there are better ones. So also like see if more responses. But also relationships between them. Okay, yeah, but it's just like so yeah, it does it, but it doesn't really do it very well. But I think Google also used it for the Google Translate, one of the early versions. It was something like this. However, there's a better one. And indeed, it is kind of, so like the problem of this network is that it forgets pretty easily. So let's say if a sentence of, let's say 300 words, and you want to translate 300 words, then we'll have a really, really hard time. Because, let's say the network will just read one word, then the next one, then the next one, and if you just insert many, many words, then it will, after a while, it will forget the first few. So that's like a problem with this network, that is really easy, it forgets really easily. So the better one is a transformer. And this network can watch all the words at the same time and will find relations. So this one's way more complicated. Like the network itself, like this one is pretty easy to understand, kinda. Or maybe also going to the harder ones, and they're also pretty hard. But transformers, there's like a lot going on. But what transformers are doing in general, they're trying to match words. So they're looking to the whole sentence. So let's say this is the whole sentence. So there are many, many words here. And the transformer can just look at all the words at the same time and will just find matches. So it will find like, oh, this word is related with this word, this one with this word. And that mechanism is called attention. Also like a famous paper of Google is called Attention is All You Need, and they explain how this works. So yeah, it does work, but there is a better one. Yeah, that's kind of good. Let's see, yes. Yeah, so this is, I think, so I showed you a few models. So what we looked at is, of course, the first one, the first feed forward. So those are just normal neurons, and just you can have many layers, pretty wide and stuff like that. Then we also looked at a convolution network, and there's like a network which is looking locally on an image, and then it's kind of like compresses the image, looking locally on the image, compresses it again, and then does that a few times, and then you have a normal neural network. Then we also looked at the autoencoder. So that's something which compresses it and then it returns it. We also looked at the GAN, kinda. So that was the one with the zebras and horses. So again, it's actually something which is, let's say, confirming if an image is correct, yes or no. And UNet is a network which is good at transforming images. So this one is, UNet is transforming images, and this part make sure that the global picture is good, and let's say these lines are for the finer details. Not only different, yeah. And of course we also look at recurrent neural network, and that's something which is inserting one word at a time. So you have one word into a neural network, recurrent neural network, and thus makes one rotation, and then another one, then another one, then another one. And I said like there's a better one for using for translation, and it's called a transformer. By the way, I have different versions of the recurrent neural network, or different versions for transformer. So these two are not meant for translation, but those two can be used for translation. So for example, also networks can have different, if you just make them a little bit differently, they can have different tasks. So these ones are not for translation, but they are still transformers and recurrent networks. But yeah, transformer is better most of the time because it can look at all the words at the same time. Yeah, I didn't talk about this one, but this is a variation of this one, and this one can also generate images, but I didn't talk about that one. So yeah, I think this is about it regarding the presentation. So if you have any questions, I'm glad to answer them. And maybe if you also like want to see like to make one of those models, I can also just like maybe make one and show you how it works. And maybe I think you probably want to see one, so I will at the same time let's also like make a compression algorithm. So I will just show you how the compression algorithm works, and then if you have more questions, then I will just answer them. Localhost. How long have you been coding? Coding? I don't know, pretty long. I started during university. So yeah, I studied physics. I have a master's in physics. So during that time I already started coding, but in MATLAB. And I finished my master's, I think, 4 years ago. And then I started doing Python and JavaScript. And yeah, I've done that for 4 years now, I think. So during my studies, I did some in MATLAB. And after my studies, I did something in Python and JavaScript mainly. And also C#, and what else? C, C++, I don't know, multiple languages. So at the same time, in the meantime, I'm going to do some coding. So let's go to a folder. GitHub, let's just make a new one. Okay. Let's go for data set. Wait, not IMDb. Where is it? MNIST. So I will first just get some images. So I will go for letters because they're easy to import. I just want to have the code to just put them in my data. Okay. So from import TensorFlow STF. So you have multiple networks which you can use for neural networks, and I use TensorFlow. Okay. Let's see. So we use the MNIST data set. Let's see. Module is not callable. It's a module. Load data. Okay, cool. Load data. Let's see if you have more questions. In what way have you used neural networks for practical applications? Yeah, so most of the time I just give courses in neural networks. But yeah, we also do some, what is it? Consulting. So one of the projects was to predict actions of customers. So let's say you have customers and they have done multiple different actions, and we have to predict a certain next action. And yeah, so that's one project we did. What else? Yeah, now we're also doing something with analyzing documents. There's also something else that's more like natural language processing. And next to that, I also have done my fun projects, let's say. You have showed that Doom game. How did you manage to show in a web page with a controller? Is the whole neural network running? Yeah, good question. So yeah, the good thing is that I can both program really well in Python and in JavaScript, so I know them really well. That helps a lot. So TensorFlow, the library I'm using, it has a JavaScript version and a Python version. So I trained the network in Python because Python is way faster with neural networks. But you can also transform you can also change the model into a JavaScript version. So I just indeed made it in a JavaScript version and I imported it in my front end. So the whole model is run in the front end, not on the back end. So when you play the game, and you actually download the neural network in your computer, and it will run locally. So also like the reason why it doesn't work in Chrome, because to run it smoothly, you need a specific library, because neural networks are very, very demanding. But in Chrome, for some reason, the library is missing, so that's why it doesn't work. But in Firefox, it does work. What kind of documents? Yeah, I think I maybe cannot say it because of NDA stuff, but let's say legal documents. Okay, so here I have images. Images. I think, right? No. And now I have images. So these are all images I have over here, and I also import some other libraries. Import pyplot, right? From pyplot lib, matplotlib, import pyplot splt, and also import numpy snp. Okay, so now I can also like show the image, show plt.imshow. So here you can see a number, so let's also make it gray. Color, oh, is it like C? No, color gray. CMap, okay, CMap, like every library has a different thing. So here you can see an image, so now we'll make an image generator. So first let's show you guys how many images I have. So here I have 60,000 images. So let's say I want to see the next one, I just insert a 1 over there. Let's say I want to see the third one, I can insert a 2 over there. So now I have images, so now I want to make a neural network which can generate images. So the model to do this is this one. Yeah, let's see, this one. So this is the one I showed you, like how you can compress images. So I will make this one. So from TensorFlow import from TensorFlow dot keras dot layers imports dense and max pooling and convolution 2D, and from TensorFlow keras.models import sequential. Okay, cool. So now I have everything I need to make a neural network. So my model of, let's call it neural network, is this one. And then let's go something. So I also showed you like VGG19. So it will be something like this model. But of course smaller, because this one's huge. But I will use convolutions and max pooling. Convolution, max pooling, convolution, max pooling, convolution, max pooling. And then I will do something like this. But then I will flip it. Oh, I also need the one which is flipped. And the flipped one is called convolution to the transpose. So I also need the transpose version. So first I have to insert the image. I mean, do the handle the image itself. So it's like this. I have to say how many filters the convolution layer needs. I have to say the kernel size, and then the strides. Yeah, let's not go into too much detail what it all means, because it's a lot. And also needs upscaling, upsampling. That's the one. Oh, upsampling 2D. So yeah. So when I go smaller, I use max pooling and convolution, and when I go bigger, I use convolution transpose and upscaling. So those are, let's say, the counterparts. So now I use max pooling. Yes. So this one makes the image twice as small. And then I will do it again and again. Oh, first, of course, I also have to make sure that the image size is good. So input shape is 28 by 28 by 1. The image is 28 by 28 pixels, and it's grayscale, so I have to say that it's 1. Then let's see the shape. I want to make sure that I don't throw away pixels. For example, now I have here 26, and then I go to 13, and then it's an uneven number, and it doesn't really work well. So I have to do some trickery to make it work. So what I can do is padding is same, and then it will go from 28, 20 to 18 to 12 to 6. Okay, this is fine. So let's just remove the last one like this. Okay, so now I have even numbers, which is nice because they're better to divide. So yeah, so what you're doing here is, let's say you have an image. Padding same means that you put zeros around it. That's you pad it with zeros. Yeah. Of course, I also need another one, which is called flatten. And then I need reshape. So now I use flatten. So you have an image, and if you put it in a neural network, you have to make one list. And flatten makes a list out of an image. And then I use dense. So now I have to determine how many values in the middle I will use. So let's go for 12, just a random number. Oh yeah, by the way, you also always need kind of activation function. Really. So this gives dynamics to your network. It all seems kind of like easy, but like when I'm doing things, like there's so many things going on, you're probably like think like what's going on. But well, I will just show you the result, and you probably will be happy. So then I have to make it original size again. Okay, let's also increase this to 32 and 64. And then I will do that. So 4 by 4 by 63 or 64. Then I also have to multiply. Wait, I have to have a dense layer, dense like this. Okay. Okay, I think I will not explain every step because there are a lot of steps. And then I need, so first one I use is convolution, so I need to start with transpose convolution. So like that. Transpose convolution. 64, 3, 3, 1, 1, and I have to do activation. Then I have to do upsampling. So this part makes it go down, so it decreased the size of the image. And now I'm going to do the increase part. So what I already did, I finished this part and this one, and now I'm doing this one. So now I'm going bigger. So I have to do upsampling, and then yeah, upsampling. The default for upsampling is 2, 2 anyway, so I don't have to do this because it's the default. But if you want to do it, let's say mention it, then it's of course nice to do it like mention it already. Activation, and of course then I have to do the last one has to do padding, so I'll also do padding right there. Upsampling, no, the last one you only have 2 downsampling, so only we need to have 2 upsampling, and then the last one it has to be image of 1 color, so I have to also do this one. So this makes sure that it just becomes 1 color. Padding is same, and I hope reshape. Oh yeah, like that. What else? Comma behind it. Okay, cool. Okay, and now I think I finished it. Yes, it works. So now you can see the model here. So the input will be 28, 28 by 1. So it will make it 28, 28, 16. 16 means the number of filters because the convolutions has a dimensionality to it. Kind of hard to explain, but yeah. So here you go down. So this is the going down part, and then it will flatten. It will go down even more. So this is going down, and this is our latent space of 12, and then I have to go up again. So this is the going up part, and this is the output. So now I have to train it. So I will train it. It's doing fit, and then I have to use my images. In order to make it my train data, it has to be reshaped to -1. 28, 28 by 1. Yeah, it's a bit hard to explain like why you have to do this, but you have. So you have to add so the only reason why I'm doing this because I have to add a dimension to it at the end, so I have to do this. So I will do fitting. Oh, I can also, by the way, make a test set. This may be also nice to do test data. So I also make a test data set, and you also that's also what you have here. So MNIST, so these are the images, and then you also have test images. And the test images, out of my head, I think, is it this one? I think these are the test images. Let's see. Yes, those are test images. Yeah, I've used it too many times, so I already kind of know the library. Okay, cool. The test images, I use that to track if my model is working. So then I do epochs, meaning, so epochs means how many times you do training. So you have the data set of 60,000 images, and epochs means like how many times you're going through all the images. So I will put it at, let's say 25. And then I have validation data. Validation, come on. Validation data is this one. Oh, and I have to do this one again. Oh yeah, by the way, the input and the output is the same. So this is actually the spot for the input, and then you have to also add the output. So the input and the output are the same. And that's because this is the input and it's also the output. So now, I hope this will work. And of course it doesn't. Oh, I have to do compile first. Yes. So let's also decrease this one. So compiling means like, what are your training conditions? Like, how do you want to train your model? So that's how you do this. So compile. Loss is mean squared error. The optimizer is Adam. And I don't need metrics. Okay, so now my model is compiled, and now I can do training. Okay, I hope it'll work. Yes, now it's training. Okay, So now it's going through all the images, as you can see, and like I said, I will do it 25 times. So afterwards, I hope it will work. So you do see that it's training, and the way you see this is by looking at the loss. So as you can see, the loss is going down, and the loss in this case means the difference. So the difference between this image and this image squared, because I use mean squared error, that's this value over here. And if it's going down, that means that the image is becoming more and more the same. So let's go. Hey, it went up here. See? It went up. Here it goes down again. So that's kind of funny. It went. Oh wait. Let's stop, because I want to also show you something. Outputs. So I also want to show you guys the outputs. So I will start over. So now we'll go and do round 1 first, because I also want to show you the training behavior. And if you do outputs, then you can see the training behavior. I have to go to work. Thank you for your explanation. Good work. Yeah, thanks. I think also this video will be on YouTube, so you can also watch afterwards the results if you want. Yeah. Oh man, why did I do 25? It takes so long time. Yes, so if you also have other questions, then you can ask them, because I have to wait, I think, 1 minute before this model's done. So it's not that long actually, but I also have a good computer, by the way. So I have an RTX 2070 card, 2070 Super card, so it's a pretty decent card. Yes. But you can also do this at home. So if you want to type along, you can probably do it. Oh yeah, by the way, if you want to do this, you also have something which is called Google Colab. And that's an environment of Google, so you can actually use the servers of Google. Let's go and have a new new notebook. So you will start here, and you can actually write code and use the servers of Google to actually do the same thing. So everything I do here, you can also do it over there, and everybody can do it. So you don't need to install Python on your computer, because you're using the computer of Google. So that's really nice. Okay. So as you can see, the loss is still going down, so it means that it's still training. As you can see 2 different losses. So this is the loss of the trained data, and this is the loss of the test data. And the best thing is to look at the loss of the test data. Oh, here it's going up again. Let's see. Here it's going down. Nice, it's still training. Training. Okay, I think it's like 20 seconds left, 15 seconds. Okay, so now it's done. So now I can use it to, so let's first test how this model, if this model trained properly. So what I will do, I will insert an image and see how well it reconstructed it. So let's go to the slides. So I'll just insert a image, and I will put it through the whole model and see how the output looks like. So let's take a image. So x test. Let's go for 3 images. So let's call my test. How is it called? I called it test data. Okay, and I will go for 3 images. So these 3 will be my testing images. So I will insert those in my neural network, and it's called predict. You can also, by the way, do it right away, but oh well. So these are my predictions. So my predictions. So these are my predictions, and now I can plot those. So let's go for plt.imshow, and okay, let's also plot the original one. So that's my tests index and my prediction. Oh wait, I cannot do it like that, of course. Then I have to do plt.show, and then I have to copy paste this, and then I do my prediction, and I will do index is 0. So I will show my first image, and then do reshape to 28 by 28. Yes. And that's just I have to do this because this library is once a different form. So here you can see the original image, and here you can see the reconstruction. As you can see, it's a little bit different. So there's loss during compression, but I think it's still looking pretty good, right? So let's also show you other ones. So let's go for the second image. So as you can see, once again, there's some loss, and let's go for the third one, or the second one, the third one, like this. I think I actually could improve it. I think I forgot to add one layer. That's why it looks a little bit different. But well, I think it's good enough. But I messed up some small part. But well. What else? Even though I messed it up, I think it looks pretty good. So, okay. So now what I can do, I can also make a random image. So what I will do, is I will only get this part. So I will remove this one and I will only keep this one. So now I can generate a image once again. Let's do that. So I have my network, and my network has many layers. And as you can see here, I want to have it from this one. So this one's interesting, but I don't want these ones. So what I will do is, let's remove a few. So 1, 2, 3, 4, 5, 6. So I have to remove the first 6. So I will go from 6 till end, and that will be my new model. Now wait, like this, and then sequential, and then like that, and let's call it NN generator. So this is my network, my image generator, and let's look at the summary. So I should, oh wait, of course I need to add a input size. Yes, okay, let's do it like that. Okay, I can also do it like this, and then predict. This is actually like a cheat method, but it works. Neural network once 28, no, not 28, 12 and 1, no, 1 and 12. To have received 12. Okay, I skipped one layer. I have to do 5 over here. Okay, 5. Cool. But received 12. Let's see. You have to go one lower? No, right? No. Yeah, okay, I did it correctly. Okay, expected to have, but received shape non-12. So I'm kind of wondering how the layers are looking like. Dot layers. Yes. Okay. Apparently, I need to go one further. Yeah. Okay. I need to go even one. I need to go from 7. Okay. So now it's looking correctly. So now I have to correct one, and now I can do the one thing I tried before. Zip. Okay. Now it works. Cool. Okay. Fine. Yes. It's kind of looking weird. Output is this one. Shape. Okay, cool. And then plt dot show imshow. Imshow this one like that. No, it's not that one. Reshape 28 like this. Okay, so this is of course an awful image. So this is apparently when you have only once. So here I have only once, and apparently, so what I did now, I put only once over there, and apparently get a horrible image. But I think if I go for zeros, that will be better. So let's go for zeros. Huh, still bad. Okay, let's check if I can go for the other one. So let's also have the other model. So the compressor. Oh no, not 7. It has to go till 7. You proved great insights about you learned. Thank you for the presentation. I have to leave now. Okay, thanks. Well, thank you for being here as well, Matthew. I almost done anyways. Okay, so now I can do predict. Let's make a prediction of a image. I will insert my test 0. See. Oh yes. Yeah. Okay. Okay. Whoa. Okay. Now I see the reason why it probably didn't work. These things. I forgot to rescale. Yes, I forgot to rescale my image. That's why. So apparently, as you can see, the values are really, really high, and that's because I forgot to rescale. So that's why you never maybe program during a stream. So apparently the values are very high, but well, it will work anyways. So let's insert those. So numpy.array, these ones, and then of course I have to do reshape. Reshape 1 minus 1. Cool. So now you have the 7 back, but now I could also like change one of those values and see what will happen. Apparently, so this is a very small one, but as you can see, this one will change the tip. So I can also like maybe change this value over there, and here it makes it, see, thinner. So as you can see now, I can already like tune things. Maybe make this 90. Let's see what happens. Oh, see? And now it makes it a little bit more bold. So yeah, this is a very fast, of course, programming exercise, but this is already working pretty well. So yeah. So this was a autoencoder. Yeah, so there can do many different things. If you have questions, then I'm happy to answer, but now you could at least see a coding exercise. I did make some mistakes for sure. So one thing I had to do actually was, one thing I forgot to do was to divide every value by 255. So that's one thing I forgot. And that's why the middle layer was a little bit weird. That's one mistake I made, and also one mistake I made, I forgot to have an activation function over here. Activation of sigmoid. So if I have to add those two, I think the result would even be better. But as you can see, it still worked. So yeah, if you have any questions, I'm happy to answer. I for sure also like thank you for being here. It was really fun, so that's nice. I can also like, yeah, it also takes time. But also like one thing you can do with this is, for example, denoising images. So let's say you add some noise on this image, you can remove the noise. That's also really fun. Okay, yeah, thank you. Thank you as well, Niru. Thank you for being there, being here. Yeah, maybe also like hope to see you during a live meetup. Like I said, we also do them in Rotterdam, Den Haag, and Amsterdam. Why do we divide by 255? Aren't all values in the same min-max range? So yeah, they are indeed in the same min-max range, but neural networks, they kind of want the input and output values in the order of -1 till 1. So that reason is because that's how it's initiated, that it's, let's say, sensitive in that area. So like I said, like I showed you, you actually don't have to do it. But if you don't do it, the training goes slower, and also actually the end result will be worse. So you want to divide them because of the initiation of the initial weights. So that's the reason why. But yeah, I think also like people are also going off the stream. So yeah, thank you again. I think also close off here and go to my house. So it was fun to have you here. So yeah, if you want to see more things, yeah, you can also go to our websites. If you want to go to my crazy projects, you can just go to my website. I also made a recipe generator. Actually, I also made a video about this today, so you can also like check it out. I also make a Pokemon generator, so you can also check this one out. Yeah, well, thank you for being here. What's it? Prabhu? I probably say it wrong. Sorry for that. Prabhu or something. But thank you for being here. That was fun. Yes. Yeah, I think I think this will be it. I will close off, and fijne dag. Have a nice evening. Bye.